So hi everyone, in this video I am going to discuss about directed graphs. So a directed graph denoted by G of V and E consists of V, a non-empty set of vertices or nodes, and E, a set of directed edges or arcs. So it is simply a graph in which the edges have a direction, and this is usually indicated with an arrow on the edge. So you can see here an illustration or an example of a directed graph. So we have nodes A, B, C, D, and E, in which some of the vertices are connected by a directed by an arrow. Okay, so suppose we have a relationship or connection between A to B, A to D, D to E, B to E, E to D, and C to E. Okay, so each edge is an ordered pair of vertices. So take note of the word ordered. So it means that when we say a directed graph, we only mean a one-way path. So, and we also said that it is an ordered pair of vertices. So in this example, we have a directed edge between A and B. So the direction is, or the order is A to B, but not A to B. So here is another example. So there is a path from E to D, but not D to E. So as mentioned, a directed graph has only a one-way path. So a directed edge U to V is said to start at U and end at V. So in these examples that we have said, so we basically mean that we start at A and end at B in B, and start in E and end in D. Okay, so can you figure out the rest of the edges in this graph? So you can do it on your own. Now, let's have another definition. So suppose we have U and V as an edge, U to V, be an edge in G. So we can visualize it like this. We have U to V, and this edge represents the connection between U to V. So, or the one-way path from U to V. So we can then say that U is the initial vertex of this edge, and U is adjacent to V. And we can also say that V is the terminal or the end, the vertex of this edge, and V is adjacent from U. Okay, so U is adjacent to V, and V is adjacent from U. Okay, and if we also have a loop, then the terminal and the initial and the terminal vertices of a loop are the same. Okay, so in this example that we have an edge between A to B. So the initial vertex here would be A, and the terminal vertex here would be B. And we can say that A is adjacent to B, and B is also adjacent from A. Okay, so let's have some more definition. Okay, so the in degree and the out na degree. So what are these in degrees and out degrees? The in degree of a vertex V, denoted by deg minus of V, is the number of edges which terminate at V. So as you already know, in a directed graph, there are directions, right? And the direction is being specified by the arrow. And if there is an edge between two vertices, then there is an initial and a terminal na vertex, right? So for example, in this B, how many edges are terminating at B? So we consider B here as our terminal na vertex, and we should count how many of the arrows are coming in. Okay, so that's one way to think of it. How many arrows are coming in? So if we count the arrows that are coming in, it is equal to 2. Okay, and for the out degree of V, on the other hand, which is denoted by deg plus of V, is the number of edges with V as the initial na vertex. Okay, so note that a loop at a vertex contributes 1 to both the in degree and the out degree of the vertex. So we have the same example here, assuming we are at the vertex B. So we are going to consider B as our initial vertex. So how many arrows are coming out of B? And we can see here that it is only 1. So we can then say that the out degree of B is equal to 1. Okay, so if you want to have like simplified, how many arrows are coming in? That is the in degree. How many arrows are coming out? That will be your out degree. Okay, so let us have this example. We have nodes A, B, C, E, D, and then F. So A, E, and C both have loops. And then between A and E, there is a way from A to E and a way from E to A. And similar for E and D, there are also 2 ways here. Okay, so now we can also see that we have an additional vertex here that is not connected to any of the other vertices. So let us try to figure out the in degrees and the out degrees of each vertex. So what would be the in degree of A? So that we have to count all those edges that are coming in, and note that we are going to count 1 for the loops, and also there is 1 edge coming from E, so the total na in degree of A is 2. And now we have to count all of the out degrees of A. So we basically have to count all those arrows or edges that are coming out of A. And we have, as we mentioned, in the loop, we have to count 1 for the in degree and to count 1 again for the out degree. Okay, since this is still considered an edge. Anyway, we have to count this as 1 and then 2, 3, and then 4, since A is adjacent to B, C, and then E. Okay, so 4. What about for B? For B, all the edges coming in is only 2 from A and then C, and the edges that are coming out is only 1, since there is only 1 edge from B to D. Now, what about for C? So for C, there are 3 edges coming in. So that is from A to D and from itself. Okay, what about the out degree of C? And we have to count the loop again, 1, and then C to B, so total of 2. What about for D? So all the arrows coming in is only 2, and that is from B and E as initial vertices. And all those edges coming out of D is also 2, since D is adjacent to C and then E. Okay, and then for E, we only have 3, so 1 for the loop and 1 for A and B, so total of 3. And all edges coming out, so we count 1 again for the loop, and then E to A and then E to D, so that is equal to 3. And then for F, since F is an isolated node or vertex, so there are no edges coming in or coming out of F. So we can then say that its in degree and out degree is equal to 0. Now let's have another theorem. So assuming we have a graph G consisting of vertices and edges, and let this be a graph with directed edges, then we can say that the total number of edges is equal to the sum of all the in degrees, and the sum of all the in degrees and the total number of edges is actually equal to the sum of all the out degrees. So these 3 are equivalent. Okay, so this first sum counts the number of outgoing edges over all the vertices, while the second sum counts the number of all incoming edges over all the vertices. So it follows that both sums equal the number of edges in the graph. Okay? Anyway, kung itagalog mo lang yan, it will be like, you can think of it like kung ilan yung lalabas, yun din yung papasok. Okay, so yun din yung number of edges natin. Now, let's go back to this example. Let us try to prove this theorem with an example. And we have already determined here the in degrees and the out degrees of each vertex, so I don't have to explain it all over again. Okay, so if we sum up all the in degrees of all the vertices and all the out degrees of all the vertices, and we can see that they are equal. Okay, they are both equal 12. Now, if we count the number of edges, so let's count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then 12. Right? So we can see that there are also 12 na edges. So we have proven that the total number of edges is equal to the total na in degree and the total na out na degree. Okay? So in the next video, we are going to discuss the complete na graphs.